se deba al carácter difusivo del radón y también al tipo de medición aplicada. Pero sí es
Student of Nuclear Engineering Department of Federal University of Minas Gerais and a member of the Monte Carlo Modeling Expert Group. And today I will present our work, Monte Carlo Modeling and Simulation of a new 3D printed phantom for whole body contour calibration. And the whole body contour calibration systems play a fundamental role in non-invasive assessment of internal radioactive contaminants in individuals, estimating the activity in the body at the time of the in vivo monitoring. And the use of biokinetic models and computational simulations allows the estimation of the incorporated activity and the distribution of absorbed doses in various organs and tissues. And the whole body contour systems traditionally utilize various detector materials such as sodium iodine scintillation detector and the high purity germanium to detect gamma radiation emitted by internal radionuclides. To accurately assess absorbed doses in internal dosimetry applications, calibration of in vivo monitoring systems is paramount. Traditionally, calibration procedures are designed in such a way that the counter rate measured by the detector of the whole body contour can be correlated with a non-standardized activity of one or more radionuclides incorporated into a anthropomorphic physical phantom. And some examples of physical models include the bottle mannequin absorption, the BOMAP phantom, this one, modulated EMA phantom, this one, and the Igor physical phantom. And usually these phantoms have a family phantom of different size, like we can see here in Igor phantoms. This is some examples. There are various phantoms for whole body calibration, but in general, their geometrical profiles predominantly comprise cylindrical and ellipsoidal shapes, approximating the cranial, thoracic, abdominal, pelvic, and limbic regions. And anatomically, whole body specific phantoms represent a promising avenue for refining calibration methodologies, enabling a more faithful emulation of human form and minimizing potential measurement discrepancies. The RFPID, that is Reference Female Phantom for Internal Dosimetry, is a new homogeneous anthropomorphic and anthropometric physical phantom, 3D printed, and ongoing, developed by the authors, by our group, and based on the reference computational phantom adult female of ICRP publication 110. So our phantom has 16 compartments 3D printed with PLA filament, and these compartments have an empty cavity inside to be filled with a tissue equivalent material mixed with a non-activity of a certified Europe 152 source. The ballistic gel was the material tissue equivalent planned for this purpose. However, since the filling process is laborious and involves risks of internal and external contamination, it is convenient to know the performance of the physical model built with the proposed materials compared with a heterogeneous human body. So here we have the RFPID physical phantom model and 3D printed. In first image we have the physical model, and there is a reference female woman with 160 centimeters of height and 60 kilograms of weight. And in second image, we have a 3D rendered image of the physical model. And third image is the transversal section of the computational model that we developed. So the aim of this work was to use the MCNP 6.2 multicolor code to simulate the homogeneous RFPAT 3D printed physical phantom, fill it with ballistic gel, and compare it to established heterogeneous RCP-AF computational voxel phantom, and exploring the system's performance across a wide range of energies and assessing its sustainability for whole bar counter calibration. The computational phantom was based on the images used in the 3D printing process, and these images were joined up to assemble the full model and have matrix dimensions of 178 per 565 per 82 cubic millimeters, and a voxel size of 3 per 3 per 3 cubic millimeters. The raw image of the full model was converted to data compatible with the MCNP code using an in-house program in C++. For the computational phantom of our phantom, entailed the utilization of three distinct materials: PLA, serving as the filament for the 3D printing process, ballistic gel, employed as the internal filling material, and external air of the surrounding environment. Due to the lack of data available in literature about the chemical composition of the gelatin used to produce the ballistic gel, a way to simulate it is as a filling material was to consider the composition of the water and the density of the experimentally obtained ballistic gel. That was 1.09 grams per cubic centimeter. And the density of PLA was obtained experimentally too. The computational phantom was positioned in beds of in vivo monitoring system at the Center of the Development of Nuclear Technology of National Commission of Nuclear Energy of Brazil. And the system was previously modeled and validated by Pacheco. The system is equipped with sodium iodine scintillator detector, and the source was uniformly distributed into the ballistic gel compartments with monoenergetic isotropic photons. And the Tele F8 card was used to evaluate the photon pulse height on sensitive volume of the detector per photon emitted in the source of the model. And the spectral data was obtained in 1024 energy bands with energy steps for 3 keV, ranging from 3 keV to 3072 keV, which simulates the configuration of sodium iodine detector for the Holy Bar counter of CGTN laboratories. The absolute efficiency for each energy was calculated as the quotient of the pulses at the photopeak channel per particle emitted at the source. And for purpose of comparison, the same geometry and particle energies of the simulations with RFPAT were conducted with the RCP-RF-AF heterogeneous phantom. But in this case, the radiation source was homogeneously distributed throughout the soft tissues of the phantom. Here we have a sagittal and transversal slice of RFPAT on the left of the image, and the same slices for RCP-AF on the right of the image. Here we have a table with the efficiency results for RFPID and RCPAF for different monoenergetic photons. And the relative errors to the simulation results were lower than 1% for all energies, except for 25 keV. For this energy, the relative error was inferior to 1.5%. Among the energy studies, the efficiency peak occurred at the energy of 250 keV. And the higher difference is in the 25 keV energy, with a difference of 31% between the both photons. The reduced detection efficiency of a sodium iodine for low energies, like the two lower density, and can be attributed to the high photon absorption in the body and in the window of the detector. Furthermore, discrepancies for this photon's energy are not a major source of concern, since sodium iodine detectors have an excessive variation in the detection efficiency in the low energy region. And in the energy ranging from 50 to 1000 keV, the differences were lower than 8%. And this energy region is important for the detection of internal contaminations using this detector, because higher efficiency, low noise, and the fact that several radionuclides of interest emit gammas in this energy range. So the use of correction factors is indicated if it results with a higher degree of accuracy are required. These factors can compensate for the deviations that may arise during whole body control system calibration at these energy levels, and could be an important step to achieving accurate dose estimation. And for energies of 1250 keV to 3000 keV were not statistically significant, since the relative errors were the same order of magnitude. Such consistency in the calibration coefficient simplifies the calculation process for those assessments in this range. This is the efficiency curve as a function of energy obtained from the table data, where we can visualize better. Its aspect aligns with the findings in previous research with the sodium iodine scintillator detector on context of the in vivo monitoring systems. Here we have some examples of this. For example, Pacheco, in his simulation regarding the content efficiency of the scintillator detector employed in this study, also observed similar curve pattern. Likewise, Lebach reported analogous curve characteristics. In their simulation work involving the EMMA Holy Body photons, spanning from pediatric to adult size, and this consistent pattern persisted across all these phantom sizes. And furthermore, Park discerned the same difference curve configuration concerning energy in their experimental setup and stimulation utilizing a male BOMAP phantom. This concordant findings emphasize the consistency of the efficiency curve shapes with respect to energy across various studies and methodologies, underscoring its applicability and the relevance in the radiation detection and monitoring. And the results demonstrated the RFPID 3D printed with PLA and filled with the ballistic gel could be used as a calibration phantom for whole body control systems. Nonetheless, when adequately filled with ballistic gel containing Europe 152, experimental validation with the physical model will be required to confirm the results of this study. And thus, future work aims to incorporate Europe 152 to the ballistic gel to fill the 16 compartments of the physical model and use it for calibration of the in vivo monitoring system of CGTN-CNN in Minas Gerais, Brazil. I'm thankful for the institutions for the financial support of FAPEMIG, CAPS, and CNPq, and the Brazilian Nuclear Technology Development Center, where this work was developed. And here is my email address for contact. I appreciate your attention for this presentation. Thank you so much.
Hi, my name is Esther Andrade. I am a master degree student in the Nuclear Engineering Department of Federal University of Minas Gerais and member of the Monte Carlo Modeling Expert Group. Today, I will present our work, Study of Ballistic Gel as a tissue substitute for using on internal dosimetry physical phantom development, specifically for whole body counter calibration. Humanoid phantoms simulate the human body when in the presence of ionizing radiation. They can be used for calibration, dosimetry, and imaging quality purposes. And to activate these phantoms must have tissue-equivalent materials, that is, materials that mimic the behavior of human tissue in interactions with ionizing radiation. And according to ICRU report 44 and 48, a material is considered tissue equivalent if its linear attenuation coefficients closely resemble those of human tissues within a specific energy range. In addition to this, the mass attenuation coefficient, the linear energy transfer, among other factors, can also be considered. But for us, the most important of them is the linear attenuation coefficient, since as it is a homogeneous phantom for calibration for whole body, there will be no density variations for various organs. And so ballistic gel has been widely used as an equivalent tissue in ballistic studies due to its mechanical properties similar to human muscle, mainly related to impact and penetration. However, studies related to its radiological properties are scarce in literature. And the whole body counter systems play a pivotal role in the in vivo monitoring of internal dosimetry in cases of internal contamination of individuals with radioactive source. And these systems normally employ a sodium iodine scintillator detector or a hyperpure germanium semiconductor detector. And its calibration is typically achieved through experimental means, utilizing physical phantoms contaminated uniformly with certified radioactive sources of known activities. And therefore, the constituent materials of these phantoms must exhibit tissue-equivalent characteristics encompassing a wide energy spectrum due to the countless radioisotopes that an individual can become contaminated with. So the objective of this study is to examine and the tissue equivalence of ballistic gel as a potential material for the fabrication of physical phantoms dedicated to the calibration of whole body quantum systems. And the investigation aims to assess the material's physical and biological properties and linear attenuation coefficients in a broad range of energy. So 5 ballistic gel samples were developed with water, glycerin, and gelatin, and then placed on molds with dimensions of 10 per 10 per 1 cubic centimeters and refrigerated at 5 degrees for 12 hours. The experimental setup consists of a sodium iodine scintillator and a radio 226 source positioned 15 centimeters apart and shielded with lead. Here we have a figure with a side view and a top view of the setup. The source is on the source is in the right size and the detector in the left side of the image, and here is the face of the detector. So first the five samples were positioned and measurements were taken and then removed one by one, thus varying the thickness of the material. 3 counts of 2 hours each were made using the GENI 2000 software for each number of samples positioned, as a way of reducing uncertainties associated with the measurements. Peak areas were determined for 8 energies of the radio 226, that is 186.1, 351.9, 609.3, 1120.3, 1759 and 2204.1 keV. And the mean of and counts per area were analyzed for each energy and each count. And the average of these 3 counts was calculated for comparison. Attenuation data was compared to water and PMMA, which are 2 well-established surrogate tissues in phantoms development. The linear attenuation coefficient was determined using this equation, where E represents the final intensity of the photon beam after passing through the material. In this work, E is the peak area obtained with a sample of thickness X, and I0 is the initial intensity of the beam, and in this work was considered the peak area without any sample. M is the linear attenuation coefficient, and X is the thickness of the material. And to determine the density of the ballistic gel, the relation between mass and volume was made. So here we have a table with the results of linear attenuation coefficients of ballistic gel for each energy analyzed, and also of water and PMMA. Here we have a difference of less than 8% for ballistic gel, except for energy 2204.1 keV, with a difference of minus 21%. And this is considerable increase in the difference may also be caused by the low detection efficiency at this energy, and in addition to the low abundance of photons emitted at this energy by the source. And higher abundance energies like 351.2 and 609.3 keV demonstrated a difference of minus 1% and 2% respectively, and water showed minus 4% for all energies, and PMMA a difference of 11% for all energies too, and the linear attenuation coefficient. So in figure 2 we can see we can see in a more visual way with the graph the data from the table shown previously in the last slide. In figure 3, the densities was considered and the mass attenuation coefficients of the materials plotted on the graph. And we can see that all materials present similar results except for the greater difference in the high energy and for the ballistic gel, with the causes already explained. Overall, evaluating the linear attenuation coefficients of greatest interest for applications of homogeneous phantoms for calibration whole body counter systems for in vivo monitoring. Water is the material with the best tissue equivalence, followed by the ballistic gel. The ballistic gel was favorable for the desired application over a wide energy range. The density calculations was 1.09 grams per cubic centimeters, and a difference of approximately 4% when compared to the muscle, that is 1.05 grams per cubic centimeters. And physical and biological analysis of the ballistic gel under different temperatures, approximately 25 degrees at room temperature and around 5 degrees at refrigeration. We have 3 points to show here. First, post-dilation, the material attains a solid non-matte consistency, and this solidity is more pronounced under refrigeration, yet exhibits limited alterations at ambient temperature, and this consistency has not changed over time. Second, a microbial proliferation typified by fungal growth becomes evident approximately 2 weeks after the material's preparation under ambient temperature conditions, extending to 3 to 4 weeks under refrigeration. This problem can be easily solved by immediately sterilizing the material with gamma irradiation or adding antibacterial and antimicrobial agents to the material received. And third, an assessment of the sample's mass at both temperatures reveals a measurable reduction in water content. This attenuation approximates 5% after a 3-week duration, and this can be resolved by placing the material in a completely sealed compartment free from any source of leakage. In general, the results reveal that this material may be used for the established purpose, and since these physical phantom types necessitates mimic tissues in a broad range of energies, and workers are still going on testing another material compositions of ballistic gel recycles, as well as investigations its radiological characteristics utilizing X-ray beams with varying qualities. I'm thankful for the institutions FAPEMIG, CAPES, and CNPq for the financial support, and the Brazilian Nuclear Technology Development Center, where this work was developed. And here is my email address for contact. I appreciate your attention for this presentation. Thank you so much.
Hello and good morning. I'm very proud to be here today at the International Symposium on Solid-State Dosimetry to share our recent study effective dose estimation due to the natural radioactivity in cosmetics and essential products for daily care sold in supermarkets in Brazil. We are a group from Brazil, from Rio de Janeiro, and we are here to share this work with you. For our introduction, studies report that many products concentrate some radionuclides because they believe that they bring some benefit to the skin. These include those that can be applied to the face as skin cream, lipids, eyeshadow, and others. So because of the contact to skin, we are studying these products and its activities. For our materials and methods, 20 samples were collected in the popular markets of Rio de Janeiro, Minas Gerais, and Brazil, so 3 different Brazilian states. And then the samples were collected randomly, weighted, and the mass measured. They were then carefully placed without compactation in 120 milliliters propylene containers with low water levels. The containers were sealed to prevent the leakage of radonium-222 and radonium-220, and left for at least 35 days in an environment with low levels of temperature and pressure variations to reach the secular equilibrium condition between the radium-238 and radium-228 with their decay products. The system that we run at our analysis, a high-pure germanium detector, and here we can see the activity concentration and their equations. Detecting norm, different high-intensity gamma peaks were used due to the secular equilibrium of the radionuclides and their descendants and are shown in the table. Here we can see the estimation of the annual effective dose to the skin according to the ICRP 60, described in the equation 6. Results here. The concentrations range from 0.9 to 47.9 for radium-226, 7.5 to 40.3 for thorium-232, and 8.5 to 271 for potassium-40. The average concentration values were 6.7 for radium-236, 4.9 for thorium-232, and 36.9 for potassium-40, and exceeded the exemption limit recommended by international agents. However, if compared to the values recommended by Unicórdoba for soil, they not exceeded the recommendation range. No sample had effective dose higher than the effective dose of some cosmetics and health products is higher than the European Commission exemption limit, which is 3,000 microsievert per year. The highest value found was in the shaving foam, which corresponds to around 1% of the limit value. The present work estimated an average of 0.35 for the number of possible cases of harmful health effects due to the radiation that could be associated with the use of this material. It's observed that the value of 2.9 cases was the highest, and it was found in the shaving foam sample. However, this value is about 3 cases out of a possibility of 150 million users of these products analyzed here. Therefore, they presented a very small number of possible cases and do not represent a radiological loss for the person's health for these products. The ICRP suggests that the stochastic effects in low-dose products make it difficult to consider them safe or dangerous for consumers for consumer use. In view of this, UniCesar introduced the concept of dose and dose rate effectiveness factor for response to doses below 100 microsievert. ICR currently uses this concept, concluding that harm at low doses should be considered half of that impact in the LNT model. Therefore, the purpose of this work is not to consider a risk to cancer, but rather to provide information about the possibility that some cases that are harmful to health and related to this. For our conclusion, the present study, the activity concentrations value of all samples were lower than the maximum recommended values, and its values can be considered safe for use. Therefore, no countermeasures should be adopted to restrict the use of these materials. However, the average number of cases of harmful effects on health observation of this material into the skin gave an average value of 0.35 cases per year in total of 150 million people, a value that attests to the information previously found on this work, which details that there is no potential health risk due to the use of these products. Therefore, in order for a conservative dose level to expose the Brazilian population, Brazilian regulatory bodies must take a position regarding the use and limit levels that each product must have, taking into consideration the regional and social facts, among others. Manufacturers must meet standards to ensure that the radiation dose to individual members of the public is low as reasonably achievable. And the authors would thank the Higher Education and Personal Improvement Coordination and the National Council for Research and Development for the financial support. Without their help, this work wouldn't be possible. Thank you for your attention and see you. And any questions, we are very open.
Buenas tardes, primero que todo quiero agradecerles por estar aquí el día de hoy. Me presento, soy Angie Salinas, hago parte del grupo de Física Nuclear Aplicada y Simulación. El trabajo de hoy se titula Caracterización de materiales no plomados para la fabricación de protectores personales en radiología. Como podemos ver, en las unidades de intervencionismo, los trabajadores ocupacionalmente expuestos, los médicos y el público están siendo irradiados en todo momento. Es por esto que se hace necesario el uso de protectores personales, como lo ven acá, que son los protectores de tiroides y los chalecos plomados. Esto para minimizar la dosis absorbida por los trabajadores ocupacionalmente expuestos. Sin embargo, estos chalecos plomados presentan algunos problemas debido a que estos chalecos son fabricados con altas cargas de plomo y el plomo pues es un material altamente tóxico. Es por esto que el objetivo de este trabajo es estudiar materiales libres de plomo que puedan reemplazar al plomo en la fabricación de estos protectores personales. Como les venía mencionando, el plomo es un material altamente tóxico, no solamente para los seres humanos, sino también para los organismos acuáticos. Además de ser un material que con el paso del tiempo pierde sus propiedades mecánicas debido a que presenta grietas, las cuales implican una mayor dosis absorbida en los trabajadores ocupacionalmente expuestos. Es por esto que se busca que los nuevos materiales libres de plomo tengan algunas ventajas como lo son la flexibilidad para no tener los problemas de los agrietamientos en los chalecos, también la dosis, una mayor dosis absorbida en los trabajadores ocupacionalmente expuestos. Se espera que estos materiales sean amigables con el medio ambiente para que la recolección de estos chalecos pues no no sea un problema ambiental. Adicional a esto, que tengan una baja densidad. Ya si estos materiales tienen una baja densidad, pues esperamos una reducción en el peso de estos chalecos. El objetivo de este trabajo es estudiar las propiedades de atenuación y protección radiológica de los materiales acá estudiados en un rango de energía entre 30 keV y 140 keV, ya que este es el rango de energía que se usa en el intervencionismo o radiodiagnóstico. Evaluaremos el posible uso de estos materiales en la fabricación de protectores personales. Luego de una amplia revisión bibliográfica, se seleccionaron 10 materiales los cuales están compuestos por siliconas universales, polímeros como el PVC y el EPDM combinados con diferentes porcentajes de peso de óxido de bismuto, tantalio, óxido de tantalio, antimonio, bismuto, tuxteno, estaño, y carburo de tantalio. La mayoría de estos materiales tienen una baja densidad, por lo que se espera que la fabricación de los chalecos no plomados tenga una ventaja frente al peso en comparación con los chalecos convencionales. En esta figura presento el esquema de la simulación que hemos realizado. Tenemos una fuente de fotones monoenergética monodireccional impactando un chaleco y dos detectores, un detector antes del chaleco y otro detector después del chaleco. Estos detectores nos indican el número de fotones que impactaron al chaleco y el número de fotones que lograron atravesar el material. Así, pues nosotros podemos determinar el coeficiente de atenuación másico. Es importante resaltar que nosotros realizamos el estudio a 11 materiales y por cada material se realizaron 55 simulaciones en un rango de energía entre 30 keV hasta 140 keV, y para tener una baja incertidumbre hemos simulado 10 millones de historias. Vale. Aquí ya en esta gráfica presento los coeficientes de atenuación másico en función de la energía para el plomo, que es el material de referencia, y 6 materiales que están compuestos por un 50% de polímeros y siliconas combinados con diferentes metales u óxidos. Nosotros encontramos que estos materiales en un rango entre 68 keV más o menos hasta los 90 keV tienen una atenuación superior o similar a la de plomo, como lo tiene la silicona universal, que es la tendencia verde, combinada con entalio, o el PVC combinado con el carburo de tantalio, y el PVC combinado con óxido de bismuto y óxido de tantalio, que son los materiales que tienen una atenuación similar o superior a la del plomo en este rango. Sin embargo, luego de los 90 keV, ningún material tiene lamentablemente una mejor atenuación que la del plomo. Ahora vienen los materiales que tienen una concentración baja de PVC y el plomo, que es el material que nosotros que deseamos reemplazar. Tenemos el coeficiente de atenuación másico en función de la energía y nos damos cuenta que el tuxteno combinado con estaño tiene una atenuación superior a la del plomo en los primeros 90 keV, y que el PVC combinado con tuxteno y estaño, que es la tendencia roja, tiene una atenuación muy similar a la del plomo, y de los 70 keV hasta los 90 keV, pues la atenuación de este material no plomado es superior a la del plomo. Ya pues los otros materiales, como lo son el EPDM y el PVC combinado con antimonio y bismuto, tienen una atenuación muy cercana a la del plomo. Nuevamente encontramos que luego de los 90 keV ningún material tiene una atenuación mayor a la del plomo. A continuación, en esta tabla tenemos los espesores necesarios para que los materiales libres de plomo tengan la misma eficiencia que un chaleco plomado. Es importante recordar que los chalecos plomados están fabricados con espesores de 0.25 o 0.5 milímetros, por lo cual un chaleco plomado puede llegar a tener un peso de 3 hasta 9 kilos aproximadamente. Esto dependerá no solamente de los espesores, sino también de los tallajes de los chalecos. Bueno, acá hay unos materiales que debemos resaltar, que son el EPDM y el PVC combinado con tungsteno y bismuto. Estos materiales tienen espesores de 1 milímetro con 1 y 2 milímetros con un peso aproximado de 2,8 kilogramos. Sin embargo, un tercer material que resalta es la combinación del PVC combinado con el tungsteno y el estaño, ya que este material pues sí tiene un mayor espesor de 2 milímetros, pero un peso de 2 kilogramos, por lo cual nos acerca a un chaleco de 0,25 o pues ya tendríamos una reducción en el peso en comparación con un chaleco de 0,5 milímetros. Es importante, bueno, aquí tenemos que tener en cuenta que estos materiales libres de plomo ya requieren algunos bastantes espesores de 3 o 4 milímetros, por lo que ya el peso va a ser de 4 kilogramos para arriba, pues y esto pues es un problema a la hora de fabricar los chalecos, y aparte pues los trabajadores que todos los días deben usar pues estos chalecos pues van a tener problemas más adelante en su salud. No sabemos cómo se vean sus posturas afectadas. Ya, bueno, tenemos el número atómico efectivo para los tres materiales que yo les mencioné que resaltaron. Aquí pues nuevamente resalta el PVC combinado con tungsteno y estaño, que tiene número atómico efectivo alto en función de la energía comparado con los polímeros combinados con antimonio y bismuto. Ya para finalizar tenemos las conclusiones. Bueno, la primera conclusión es que los compuestos que nosotros estudiamos tienen buenas propiedades de atenuación en un rango de 30 keV hasta los 90 keV. Desafortunadamente, ningún material que nosotros estudiamos acá tiene una mejor atenuación después de los 90 keV. Es decir, que luego de los 90 keV, el mejor material sigue siendo el plomo. Además, se debe mencionar que estos materiales libres de plomo pues presentan problemas en la fabricación, ya que pues debido pues al aumento del peso y de los espesores de estos chalecos. Además, se debe recalcar que los procesos de interacción, radiación con los materiales no plomados fue caracterizado por el número atómico efectivo, y encontramos que el número atómico efectivo disminuyó conforme aumentó la energía de los fotones, que pues fue el mismo comportamiento que presentaron los coeficientes de atenuación másico para cada material que nosotros hemos estudiado. También encontramos que los protectores que podrían ser fabricados con polímeros y combinados con antimonio y bismuto, y el PVC combinado con tungsteno y estaño, presentarían una reducción en el peso, serían materiales flexibles, tendrían una atenuación similar a la convencional, una equivalencia en plomo superior a la que se requiere, que es de 0,25 milímetros, serían materiales amigables con el medio ambiente, y según lo que han reportado varios investigadores, serían materiales que tendrían buenas características mecánicas y serían materiales económicos. Sin embargo, no se puede olvidar los problemas tecnológicos que representan la fabricación de estos chalecos no plomados. Atenuación similar a la superior, tiene un número efectivo atómico alto, y lo más importante, es un material no tóxico. Estas son las razones por las cuales este material es un material muy prometedor para ser evaluado en la fabricación de protectores personales en radiología. Sin embargo, no se puede olvidar pues que no existe un material que tenga mejores características que el plomo. Las referencias de
Hello everybody, good afternoon. My name is Mariana, and I will go to present today the work called G0306, title Effect of high gamma dose irradiation on the structure of wax starch. I'm a PhD student at the Department of Nuclear Engineering from Universidad Federal of Minas Gerais, Brazil, and my advisor is Professor Adriana Batista and co-advisor Professor Ricardo de Souza. The topics will be presented in order of equivalence to working stencil. Firstly, I will give you a brief contextualization, then I will present the methodology used and results achieved, making a discussion of the results simultaneously, and next the conclusions and acknowledgements and references. Well, what is the starch? It is a natural polymer widely used in various types of industry, not only food industry, but in a paper-making, pharmaceutical, and textiles industries, as adhesive or binder. And this polymer, a polysaccharide, consists of two main components, amylose and amylopectin, that differ, like we could see at figure 1, in terms of chemical structure, where amylose is linear and amylopectin branched. And there is a range of sources of starch, like potato, cassava, rice, but one of the most sources is corn, and its wax form contains more amylopectin, which is more stable to retrogradation, a desirable reaction in some cases, such as the raging of bread. And due to limitations for application in its native form, like low stability to changes in temperature, pH, shear, modifications methods, chemical, physical, and enzymatic process have been developed. Among these methods, irradiation has the advantage of being relatively fast, requiring minimal sample preparation, safe, economical, viable, and the final product obtained is free of toxic residues. In particular, gamma irradiation can be used to modify starch, the case of this work, and this physical technique allows change of function and process characteristics, enabling cross-linking, grafting, and degradation in the polymer, which will depend on the dose of irradiation, proportion between amylose, amylopectin, and starch origin. By this process, modifications like increase of solubility, decrease of viscosity, and molecular height can be achieved. Research on corn starch irradiation explores very low doses of irradiation, typically below 100 kg. Then, the objective of this work was preliminary study the effect of gamma irradiation in high doses of 500 kg on the structure of corn starch, mainly wax starch. So, three materials, commercial starch, wax starch, and cationic wax starch, was studied before and after irradiation. First, the three materials studied were subjected to irradiation at a dose of 500 kg, and then the characterization analyses made were by Fourier transform infrared spectroscopy for analyze the changes in chemical groups, scanning electron microscopy to verify the morphology of the grains, and thermal gravimetric analysis to study the temperature stability of the starches. Lastly, a qualitative test using Lugol's iodine was performed to compare proportions of amylose and amylopectin of the different materials. First, the results obtained by spectroscopy changes between peaks obtained by the spectrum of all materials before and after irradiation, as you can see by figure 2, where for each image are the curves for material irradiated and non-irradiated. In comparison, the starch is composed of primary and secondary hydroxyl groups and contains carboxylate ion, and when subject to gamma irradiation, starch structures could be altered through fragmentation and cross-linking. So, analyzing the images, it is possible to note a band around 3,300 per centimeters for non-irradiated starches attributed to hydroxyl group strategy, which is correlated to hydrophilicity of the starch, modified for irradiated ones, presenting peak broadening in shifts, as well group Ca2 around 3,000 per centimeters. Band in the region of 1,000 per centimeters can also be highlighted for irradiated starches, which are related to an aldehyde bending vibration, much more pronounced for them. The images obtained by microscopy showed that the studied starch grains have a round or polyhedral morphology, with sizes varying from approximately 5 to 20 micrometers. And while commercial starch did not have its morphology greatly affected after irradiation, the waxy grains appear to have agglomerated, forming small polymerical groups, not identifying pronounced grain shear, like is possible to see in figure 3, letters D, E, F. That could be justified by the fact that waxy samples are more strongly affected by gamma irradiation, because the amylopectin fraction is the most affected. Table 1 shows that the main mass loss for all samples occur around 300 Celsius degree. The residues obtained for all irradiated samples was higher than non-irradiated, with the largest difference identified for commercial starch at 6.4%. The difference for waxy starches being similar between them, about 2%. As you can see by the data, there is an increasing of mass loss from cationic waxy starch irradiated from commercial starch. The increase in the residual mass for irradiated samples may be related to cross-linking process that may have occurred between polymer chains, leading to greater stability of the materials to temperature changes. Finally, a qualitative iodine test was carried out using LUGO, which is capable to form different colors complexes depending on the predominant type of polysaccharide in solution. Leads to blue in presence of amylose and brown in presence of amylopectin. The test showed that even after irradiation, the samples that contained a great amount of amylopectin, the waxy starches, becoming brownish red in the presence of LUGO, and the changing observed was in the intensity of the color obtained after irradiation, which may be related to solubility of starch, the same happening for starch with a higher amylose content. Between waxy starches, a variation in the color tone is noted, but both turned brown in the presence of LUGO. Then can be concluded that the effects of a high dose of gamma irradiation on the structure of starches was studied, according to our objective for this work. But there are many questions to explore yet, and for future works, new investigations must be carried out through other analyses like X-ray diffraction and UV spectroscopy. To summarize, infrared spectrum shows changes between the spectra of all materials after irradiation and indicative of modification in functional groups. Microscopy shows that in morphology for starch shows changes in morphology for starch grains, mainly wax type, being the three similar before irradiation. The thermogravimetry shows that the residue obtained increased for all irradiated samples, indicating a possible crosslink. And Lugol's iodine test shows that irradiated samples always present a more intense color, and that commercial starch was blue, wax starch brown, and cationic wax starch also brown but dark. And that's it. I would like to thank the financial support of the FAPEMIG, CAPES, and CNPq, and I also thank CDNTN and LCP Nano by the analysis, and IQR, which provided the wax starch samples. The references used for this work and thank you for your attention. Any doubts, suggestions, and comments, please contact me by email.
Hello, good evening. My name is Rose Sofia de Freitas Dan. I am a PhD student in nuclear engineering at Universidade Federal do Rio de Janeiro, Brazil. Today, I'm here representing my research group with the paper called Application of Americium Beryllium 241 and Artificial Neural Network to Predict Volume Fraction in Multiphase Systems. In the oil industry, it is common the occurrence of multi-phase flows, particularly during offshore oil extraction, where water and gas are also present alongside oil. The fluids are transported simultaneously from the reservoir rock to the separation units using conventional meters. However, this approach has some drawbacks, such as long execution times, high costs, and complex maintenance procedures. Therefore, multiphase meters are a valuable solution as they eliminate the need for phase separation, allowing, for example, the identification of flow patterns and the prediction of fluid volume fractions. Many types of multiphase meters have been extensively explored, including conventional meters and nuclear methods. Nuclear techniques, particularly neutron attenuation and scattering, offer reliable measurement, allow real-time measurements under normal operation conditions. Prompt gamma neutron activation analysis is a well-established non-destructive method used for chemical analysis. It exposes materials to neutron beams, leading to gamma radiation emissions that reveal the chemical elements and their concentrations. The high-energy gamma rays generated by neutron interaction can be used to identify fluid presence and volume fractions. However, multiphase flows are complex due to factors like varying phase velocities and interactions, posing challenge for parameter extraction. Therefore, this study proposes the use of artificial neural networks to interpret prompt gamma ray spectra to predict volume fraction of fluids in three-phase systems. Therefore, the aim of this study was to demonstrate that combining prompt gamma neutron activation analysis technique with artificial neural networks can effectively detect the presence of fluids and quantify their volume fractions. And how did we propose to do this? Well, first, we used the MCNP6 code to develop a simulated measurement geometry composed by tube fluids detector and an americium beryllium 241 flat source. Inside the tub, there is an annular flow regime composed of gas, oil, and salt water. The prompt gamma rays are recorded and counted by a detector, which is a spherical surface in a 4-pi geometry. Thus, the photons of all energies emitted in all directions are detected, and thus the computational time is minimized. Gamma radiation detection was performed using MCNP6 command line tally F1, recording the energy spectrum from 10 keV to 10 MeV. The volume fractions of the fluids range from 0 to 100% in steps of 5%, totaling 210 simulations. Then the next step was to build an artificial neural network to interpret the prompt gamma ray spectra to predict the volume fraction of the fluids. So in our study, the input data are the spectra with 189 neurons, and the output are the volume fractions of all fluids, gas, oil, and salt water, representing 3 neurons. This network has 2 hidden layers with 80 neurons each, and both layers have logistic activation function. The cross-validation method was used trying to minimize overfitting. Thus, the original dataset was divided into 3 subsets: training, test, and validation. So we are going to show the main results of this study. Initially, the simulations were performed for a single fluid in the tub. Then the simulations were performed with the 3 fluids simultaneously inside the tub, varying the volume fraction of each fluid. This figure shows an example of a prompt gamma ray spectrum for a simulation with all the fluids present in the tub. In this example, we have 35.5% of salt water, 29.40% of oil, and 35.1% of gas. The chemical elements and their prompt gamma rays are iron, hydrogen, oxygen, and carbon. Well, the validation subset is used as a final evaluation of the network. So, we are focusing on this subset for the following results. This figure shows the comparison between the MCNP6 data and the predicted values from the network. it is possible to observe that the network can properly predict the volume fractions of all fluids, gas, saltwater, and oil, for data that was not used in the network training phase. Moreover, it is possible to classify the network prediction in relative error intervals. So the network achieved more than 92% of the cases with relative errors below 5% for all fluids and volume fractions used in this study. Another indication of good network convergence is that the value of the regression coefficient close to 1. This coefficient was obtained using the least squares method. So we can conclude that for the proposed geometry and for the neutron spectrum of a polarenergetic neutron source used to generate prompt gamma ray spectra, more than 92% of all fluids had relative errors below 5%. The prompt gamma neutron activation analysis technique has the advantage of generating gamma rays of energies corresponding to the target chemical elements. For this reason, its spectrum that represented the presence of a fluid contains enough information to capture patterns that and can be related to the respective volume fraction, which enables adequate training of the network. The neutron source used in this study has a very long half-life, and as part of a measurement system, would allow its use for a long time without the need for replacement, making the system very interesting in the application proposed in this study. The authors gratefully acknowledge the financial support from Coordenação de Aperfeiçoamento de Pessoal de Nível Superior, from Conselho Nacional de Desenvolvimento Científico e Tecnológico. Thanks also to Instituto Luiz Alberto Coimbra de Pós-Graduação e Pesquisa de Engenharia and to Instituto de Engenharia Nuclear. Here I leave our contact information in case any of you have questions. Thank you very much.
Olá, buenas tardes, es un honor estar aquí hoy. Mi nombre es Isabela y yo soy doutoranda en Engenharia Nuclear en Universidad Federal do Rio de Janeiro. Me complace compartir minha investigação com vocês hoje. O título de minha apresentação é Monitor Impact Assembly of Nuclear Power Plant pré-operacional em current condições. Durante minha charla vou a informe introdução, metodologia, resultados, conclusões finais. Em cambio climático é uma realidade. Em 2021, as emissões de dióxido de carbono relacionadas com a energia alcançaram um recorde de 36 milhões de toneladas, impulsionado pelo crescimento da população mundial, o desenvolvimento econômico de diversos países e a melhora da qualidade de vida. E o aumento da demanda de eletricidade é inevitável. Por lo tanto, a energia nuclear é uma excelente alternativa para mitigar as emissões de gases de efeito invernadeiro e é considerada como energia verde por as Nações Unidas. Además, contribui ao logro de los objetivos de desenvolvimento sustentável. Esse trabalho aborda o impacto ambiental de uma central nuclear, comparando as condições prévias à la operação e as condições atuais de los radionúcleos em muestras de sedimentos marinhos. Para lograr o objetivo desse trabalho, se selecionou uma área de estudo, se recopilaram muestras de sedimentos marinhos e esta muestra de sedimentos se preparou para utilizar em equipo de espectrometria gama com o fim de obter informação sobre os radionúcleos de interesse para logo compará-la com os dados informados em análise prévia à operação da central nuclear Almirante Álvaro Alberto. Las centrais nucleares de Angra 1 e Angra 2, em conjunto, conformam a central nuclear Almirante Álvaro Alberto, CNAAA. Utilizam reator de tipo reator de água a pressão e geram eletricidade com uma potência de aproximadamente 626 a 1.352 megawatts elétricos, respectivamente. Sua operação começou em 1985, Angra 1, e em ano 2000, Angra 2. E a empresa encarregada de sua operação é eletronuclear. A CNAA está ubicada em o município de Angra dos Reis, em o estado de Rio de Janeiro. O lugar de recolocação de sedimento marinho foi lançada de Piraquara, que elas via de descarga de efluentes líquidos de esfriamento de los reatores PWR de Angra 1 e Angra 2. O lecho de la enseada se caracteriza por ser uma pequena llanura sedimentária com uma entrada de sedimento limitada e sua topografia cercana é ligeiramente inclinada, própria de zonas costeiras, sem entrada de rios, características típicas de enseadas. As temperaturas de água variam entre 23 e 31 e o clima local se classifica como subtropical, com duas estações distintas, uma estação seca que ocorre de julho a dezembro e uma estação chuvosa de janeiro a junho. A precipitação média anual na região supera se recolectaram 3 a 5 de sedimento lecho superficial a 10 centímetros de profundidade, utilizando uma draga tipo Van Bene e contenedores de polietileno. E o Laboratório de Análises Ambientais e de Simulação Computacional, LASC, ubicado na Universidade Federal do Rio de Janeiro, se separou aproximadamente 1 kg para o processo de secado em uma estufa a 80 graus durante 48 horas, obtendo um peso constante. Com o propósito de levar a cabo em análise mediante espectrometria gama, as amostras se trituraram e se transferiram alíquotas de aproximadamente 300 gramos de sedimento a recipiente de polietileno, os quais se selaram hermeticamente e se almacenaram durante aproximadamente 35 dias para alcançar o equilíbrio radioativo. La muestra fue analizada utilizando un electrodo germanio hiperpuro con una eficiencia relativa de 30% de la marca cámara, junto con los dispositivos electrónicos asociados. El tiempo de conteo para obtener el espectro de la muestra fue de 28.800 segundos. Se determinó la actividad del pico de 911,6 keV de actínio 228 para el potasio 40 a partir de su propio fotopico de 1460,8 keV. Además, se emplea un informe de preoperación en la central nuclear, tal como se ilustra aquí. Los resultados abordados se dividen en nivel de radionúclidos previos a la operación y nivel de radionúclidos estudio actual. Aqui se apresentam os dados do informe pré-operacional de los níveis de actividade de los radionúclidos de potássio 40 em azul e actínio 228 em rojo, como se mostra em el gráfico. Aqui se apresentam os dados atuais correspondentes a 2022 de los níveis de actividade de los radionúclidos, potássio 40 em azul e actínio 228 em rojo, como se mostra em el gráfico. Em la muestras analisadas que inclui os níveis de actividade de los radionúclidos, se comparou os resultados obtidos em 2022 com os de período pré-operacional, os resultados obtidos atual resultaram compatíveis com os valores do período pré-operacional. Se pode concluir que durante o mês de setembro de 2022 não houve impacto radiológico ao meio ambiente provocado por la operação das centrais nucleares Angra 1 e Angra 2. Además, todos os resultados obtidos em 2022 estão em linha com os valores históricos. Portanto, os análises realizados indicam a estabilidade e ausência de impacto significativo das centrais nucleares Angra 1 e Angra 2 ao meio ambiente em setembro de 2022, respaldando dados históricos e reforçando a seguridade radiológica de estas instalações. Para finalizar, desejo expressar meu agradecimento às agências de financiamento CNPq, CAPES, FAPERJ e ao laboratório LASC que contribuíram na execução de este estudo. Quero agradecer por esta oportunidade de compartilhar minha investigação. Assim mesmo, me encontro à disposição para qualquer consulta adicional através de los seguintes métodos de contato: e-mail, LinkedIn. Olá, buenas tardes, é honor estar aqui hoje Mi nombre es Isabela, eu sou doutoranda em Engenharia Nuclear em Universidade Federal do Rio de Janeiro. Me complace compartilhar minha investigação com vocês hoje. Com o título de minha apresentação, no seguinte slide. Durante mi charla voy a informar introdução, metodologia, resultados, conclusões finais. Em princípio, de se fazer referência a duas fontes de radionúclidos naturais e artificiais, a presença de radioatividade é uma característica ubíqua na corteza terrestre. Os radionúclidos de origem natural se manifestam de maneira generalizada em diversos compartimentos ambientais, já que é inerente ao entorno terrestre. Os sedimentos marinhos desempenham um papel crucial como um dos principais reservórios para uma ampla gama de contaminantes ambientais, constituindo um depósito natural de grande valor. É imperativo destacar que os sedimentos marinhos também têm um papel fundamental na preservação de registros ambientais, lo que permite uma análise detalhada de los cambios que ha ocorrido em ambiente ao longo do tempo, assim como de los distúrbios antropogênicos ocorridos em épocas passadas. A central nuclear Almirante Álvaro Alberto CNAA alberga as plantas nucleares de Angra 1 e Angra 2 em funcionamento. Estas centrais nucleares contam com uma planta de esfriamento que utiliza água captada em Itaúna e que é liberada em la Bahia de Piraquara de Fora. La monitorização de los radionúclidos em este lugar se considera crucial para a investigação do impacto radiológico ambiental, já que seriam os primeiros em indicar um aumento na contaminação em el medio marinho. Os dados de investigação sobre a concentração de radionúclidos naturais e ou antropogênicos em los sedimentos costeiros de ambientes tropicais são escassos. Esta investigação tem como objetivo geral contribuir proporcionando informação importante para reduzir a brecha existente em si, aumentar o conhecimento e a compreensão dos impactos dos radionúclidos em los sedimentos costeiros em ambientes sometidos à intempérie e com altas temperaturas ambientais como os se encontra em Brasil. A metodologia segue os seguintes passos: seleção da zona de estudo, coleção de muestras de sedimentos marinhos, preparação das amostras de sedimento para suas análises mediante espectrometria gama com o propósito de adquirir informação sobre os radionúclidos de interesse. Nas centrais nucleares, Angra 1 e Angra 2, em conjunto conforme de la CNAA, utilizando reatores do tipo reactor de água a pressão, PWR, e generam eletricidade com uma potência de aproximadamente 626 megawatts e 1.352 megawatts, respectivamente. Sua operação começou em 1985, Angra 1, e em ano 2000, Angra 2. E a empresa encarregada de sua operação é eletronuclear. La CNAA está ubicada em o município de Angra dos Reis, em el estado de Rio de Janeiro, em lugar de recolección de sedimentos marinhos por la enseada Piraquara de Fora, que es la vía de descarga de efluentes líquidos de enfriamiento de los reactores. El lecho de la enseada se caracteriza por ser una pequeña laguna sedimentaria con una entrada de sedimentos limitada e sua topografia cercana é ligeiramente inclinada, própria de zonas costeiras, sem entradas de rios, característica típica de enseada. As temperaturas de água variam entre 23 e 31 graus e o clima local se classificam como subtropical, com 2 estações distintas. Uma estação seca, que ocorre de julho a dezembro, e uma estação chuvosa de janeiro a junho. A precipitação média anual na região supera os 2.000 milímetros. Ocho muestras de sedimento superficial, 10 centímetros de profundidade, se recolectaram em uma quadricular de 250 metros, utilizando muestrador Van Ven. Logo se empecaram de 3 kg de las muestras em contenedores. Se levaram a cabo análises físico-químicos in situ mediante a medição direta de los parâmetros com a ajuda de uma sonda multiparamétrica. Inclui temperatura e salinidades. La informação compilada inclui temperatura e salinidade. Em el laboratório, a amostra de sedimentos se subdividiram para su secado em uma estufa a uma temperatura aproximadamente 80 graus durante 48 horas, hasta alcançar um peso constante. Posteriormente se trituraram. Para análise mediante espectrometria grama, se transferiram alíquotas de aproximadamente 300 gramos de los sedimentos a recipientes de polietileno, los cuales se selaram e permaneceram durante aproximadamente 35 dias para alcançar o equilíbrio radioativo secular. Las muestras fueron analizadas utilizando un detector de manipulación puro con una eficiencia relativa de 30% de la marca Canberra, junto con los dispositivos electrónicos asociados. El tiempo de conteo para obtener el espectro de la muestra fue de 28.800 segundos. Las concentraciones de actividad de las series de uranio y torio se evaluaron asumiendo que se establece un equilibrio secular entre los padres de su producción de desintegración. La actividad de adio 228 se derivó de un pico de 911,6 keV de actinio. Adio 226 se utilizou el pico de 609,3 keV de bismuto. Potasio 40, Las actividades se obtuvieron a partir de su propio fotopico de 1460,8 Kelvin. Las concentraciones de actividad, las incertidumbres se determinaron de acuerdo con la incertidumbre estadística de las áreas de los picos proporcionada por el software DN 2000. Los análisis de sitios se muestran en la tabla con un análisis estadístico descriptivo de los parámetros, temperatura y salinidad de los sedimentos. En ella, la temperatura de agua y salinidad presentaron una media de 25 grados y 3,3% respectivamente. Las concentraciones de actividad de los radionúclidos de ocurrencia natural se presentaron a través de una estadística descriptiva en la tabla 2. Mientras que las concentraciones de actividad de los radionúclidos naturales se encuentran dentro del rango informado a nivel mundial, es decir, 35, 30 y 400 becquerel por kilograma, respectivamente. Las actividades de concentración promedio y la desviación estará para radio 228 y radio 226 de potasio fueron 20, 16 y 476 becquerel por quilo de peso seco, respectivamente. La distribución de los radionúcleos se puede observar en la figura adyacente. Por tanto, mientras las concentraciones de actividad de los radionúclidos encontram dentro do rango informado a nível mundial. La tasa de dosis absorvida de radionúclidos naturales en la tabla 3 se apresenta resultado de los peligros radiológicos de la radioactividad natural en esta región, los cuales se estiman mediante la tasa de dosis absorbida y la dosis efectiva anual. Las tasas de dosis absorbida de radionúclidos naturales foi determinada para o sedimento costeiro e se encontrou que era inferior ao valor promedio mundial de 51 nanograms por hora. Los valores de dosis efectiva anual determinados também encontram inferior ao valor promedio mundial. Com o fim de alcançar o propósito de estudo, os radionúclidos analisados apresentaram concentração de atividade dentro do rango de los valores promedidos a nível mundial. Se evaluaram os riesgos radiológicos mediante a estimação da tasa de dose absorvida de radiação gama externa e a dose retida efectiva anual. Para finalizar, desde expressar meu agradecimento às agências de financiamento, o laboratório contribuiu na realização de este estudo. Para finalizar, desejo expressar meu agradecimento às agências de financiamento e laboratório de contribuir na execução desse estudo. Desejo contato information.
Hi there, my name is Lucas and I'm here today to talk about the specific activities of the natural radionuclides in solid and liquid cacao fractions. And to present myself, my name is Lucas, and I'd like to say thanks to the ISST. And just to illustrate, this is myself, and we are a group from Brazil, from Rio de Janeiro. To start, I would like to present what cacao is and to make a small introduction before going to the result. Basically, cacao, it's a pod. The cacao fruits that can colorful, they can vary from purple to yellow, collected on the cacao tree that is it's a tree that is kind of big. It can achieve 4 meters. We have a more detailed image of the cacao pod and the cacao bean. In the right peak we have the cacao bean dry, and in the left peak we have also the cacao bean dry, but we can see here that's dry, but the pod of the bean is still there. And this is a pic that I took that is to illustrate better what are the fractions of the cacao. For example, we have here the endocarp, we have the seeds, we have the pulp, we have the placenta, that is that structure that stays in the middle. We have the funicle, that are the structures that keep the seeds in the right place that they should be. We have the exocarp, that is a colorful fraction of the cacao pod. And how we are at the methodology, so we use six samples of cacao pods to illustrate better what we have done to analyze this cacao pod in a radiometric field. We had the cacao pod first, and then we separate the fractions of the cacao. First, we remove the exocarp, that is that skin of the pod that is very colorful, and then we put it at a stove to dry it, to take the humidity. We removed the exocarp. We went to the separation of the internal fractions of the cacao pod, the seeds, the pulps, the placenta, and the funiculus. The seeds and the pulps were separated. The seeds were also to the stove, and the placenta and funicle also to the stove. The pulp, it was a very liquid fraction, so we couldn't let it to the stove, so we needed to freeze it. With all that 7 samples of pods, we arrived to these other samples. So, for example, we had, 10 grams of the exocarp of the first sample of cacao pod. So we mixed all samples to become one new sample. For example, here we have the endocarp and the total of the 6 cacao pod samples. In the end, we just had 46 grams of the exocarp. So we mixed that samples together because if we do everything together, we wouldn't have enough volume and density to do the radiometric analysis. We also did that to the bulb, but we run also some physical chemical analysis of the bulb, for example, the pH. Then basically we had these other samples, and of course we, as shown here, after the stove and after being totally dry, we sealed everything, and we wait to achieve the secular equilibrium of 30 days. And here is a photography of the samples for this study package in 250 milliliters polypropylene jars that was sealed, and all samples were freezed to prevent the degradation by microorganisms. And this is the system that we have used to run the radiometric analysis. That were the peaks that we use it, and we calculate specific activities with that formula. The effective dose that we calculated use the ICRP effective dose coefficients. And our results, we can find out that the exocarp had highest activity concentration of potassium 40. The second highest activity concentration was the placenta and the funicle, and the third highest activity concentrations were the exocarp. And we can see that the seeds or the grains, they were very close. For the results, we would imagine that the seeds were the most activity concentration because the seeds have the highest activity, the highest biological activity in the meaning of the reproduction of the plants. So if you think that the seeds will make the reproduction, we also think that they need more nutrients. And what we actually find out here is that, for example, for potassium 40, we have the activity concentration. But in another hand, we also run an ash content percentage. And we find out the same results. For example, the endocarp had the highest activity concentration, and meanwhile, the ash content also had the highest activity concentration, followed by placenta and funiculum, that it's the same with the potassium 40, and followed after by the exocarp, that is the third highest in the activity concentration, but also the third highest in ash content. We can see also here that the seeds or the grains had the same action, the same results as the activity concentration. Of course, they are different units, but it just shows that potassium 40 activity concentration, we confirm the activity concentration of potassium 40, because if the ash content measure the nutrients and one of these nutrients is potassium, the ash content just confirms the potassium 40 activity concentrations. And then we go to the hydrogen 226, and it's curious because, for example, the activity concentration of the potassium 40 is the highest in the endocarp, but meanwhile in the hydrogen 226, the activity concentration of the endocarp is the lowest. And for the seeds, we have very close values. And we can see here that the highest effective dose is the hydrogen 226. But it's interesting because, for example, the activity concentration of the potassium 40 is 50 times the activity concentration of hydrogen 228, and the activity concentration of the potassium 40 is 10 times higher than the activity concentration of the hydrogen 226. And to answer that question, is we back to the effective dose coefficients by the ECRP, for example. So basically, that's because the effective dose coefficients, for example, we can see that the effective coefficient of hydrogen 228 is almost 100 times bigger than the effective dose coefficient of potassium 40. And that's why we have just so high effective dose of hydrogen 228. And the conclusion we have is that we just confirmed the acidity in the pulps. We also concluded that 40K is more present in the fence structures compared to the grains or the seeds. The results of the ash contents show the similarity to those obtained for. And the effective dose of hydrogen 208 is twice the potassium 40 effective dose, despite its activity being 50 times lower. And for the future of this work, we expected to run more physical-chemical analysis. We expected to X-ray fluorescence. We already run this analysis, but we didn't have enough time to put on this work. We also expected to study soil and to analyze how much of that transfer of that hydronucleides goes to the pod, from the soil to the pod. Basically, that's the end. So I would like to say thank you to the ISSSD again. And it's always a pleasure to be here, and we are very open to any questions. Thank you.
Hello, dear colleagues. My name is Alexey Demin. I am a student of Tomsk Polytechnic University in Russia. The topic of my report is neutron pumping of active medium formed by gadolinium isotopes 155 and 156 pair, a feasibility study. The possibility of creating technical means for controlling the process of accumulation and conversion of the energy of thermal and epithermal neutrons into the energy of monoenergetic photons emissions due to neutron pumping of active medium consisting of nuclei with long-lived isomeric states is studied in this work. The control of the process of energy accumulation and conversion in isomeric states of nuclei makes it possible to create a new generation of technology for generating coherent radiation with parameters that ensure its application in nuclear and radiation physics problems. For example, a device generating radiation with a wavelength of less than 1 angstrom and the energy of 10 to 12 megaelectron volts can be used as a nuclear excited coherent radiation source to study the properties and structure of matter. The installation considered in this paper consists of a plasma source of deuterium-tritium neutrons, a multiplying subcritical blanket, and an active medium formed by gadolinium oxide. Plasma neutron source belongs to the class of axially symmetric open magnetic traps. Its main operational parameters are shown in the table on the slide. It is used here as a source of pulsed deuterium-tritium neutrons. This installation is a real-life installation, geographically located at the Novosibirsk Institute of Nuclear Physics, where experiments on plasma retention in magnetic fields are carried out. A multiplying subcritical blanket is the core of a high-temperature gas-cooled reactor, modified for a plasma neutron source. The blanket is used to multiply the pulsed neutron flux to the level required for pumping the active medium. The blanket is assembled from unified hexagonal fuel and fuel-free graphite blocks. Helium is used as heat carrier. The multiplying part of the blanket is assembled from fuel and non-fuel columns, each of which consists of 5 blocks, where the upper and lower are reflector. 3 fuel or non-fuel blocks are coaxially placed between the upper and lower reflector blocks. Fuel and fuel-free blocks are graphite prisms with a height of 800 mm, each of which has 7 holes for the coolant. The upper and lower reflector is similar graphite prism with a height of 300 mm. The fuel blocks contain 76 additional holes designed for the installation of fuel elements. Due to the lack of heat sources on the periphery of the blanket, graphite blocks with 7 coolant holes in this area have been replaced with the similar ones, but with 1 central hole. The calculated value of multiplication factor is 0.95. In order to maintain the subcritical multiplication factor and thermal power at constant level, the plasma neutron source have to continuously supply the blanket with neutrons. To study neutron capture reaction by active medium and the mechanism of energy storage and conversion, a variable geometry beam shaping assembly and thermal neutron imaging system are used. The variable geometry assembly consists of a system of moderating filters and selective plates, designed to concentrate and form radiation with the required parameters. Its internal volume is designed to have an elliptical shape. The principle of operation of such module is based on the effect of neutron diffusion and reflection. The variable assembly allows to select the parameters of neutron flux necessary for the following conversion of their energy into the energy of monochromatic gamma radiation for the desired neutron generation mode. As an active medium is proposed to use a pair of stable gadolinium isotopes with mass numbers 155 and 156. Gadolinium is a rare earth element. The element features the largest capture cross-section for thermal neutrons among all stable elements. The energy conversion takes place inside the active medium formed by isotopically modified gadolinium oxide. Due to neutron radiation capture reaction on gadolinium-155 nuclei and following decay of isomeric state of gadolinium-156 isotope with the emission of coherent gamma radiation. The de-excitation of composite nucleus is a cascade process and can occur both as a result of a direct transition to a metastable level and as a result of a cascade of gamma transitions. Due to such cascade transitions, as well as due to the unique combination of absorbing properties of a pair of gadolinium isotopes 155 and 156, the rate of formation of metastable gadolinium nuclei 156M is significantly higher than their decay and de-excitation rates. The target isomer has a half-life of 1.3 microseconds and decays with the emission of a gamma-ray quantum with an energy of 2.1376 megaelectronvolts. The conditions required for pumping the active medium are shown on the slide. An additional channel for the formation of metastable gadolinium-156 nuclei, according to our purposed scheme, is the transition of nuclei from an intermediate state which is formed at a level slightly below the metastable one. The additional energy required for the formation of metastable gadolinium-156 isomer is occurred by the nucleus in the neutron inelastic scattering reaction. These features of gadolinium isotopes under certain pulsed mode of irradiation with a neutron flux with the energy less than 10 electron volts allow creating conditions for the accumulation and release of gamma radiation. Neutron flux mapping is carried out by the same neutron radiation capture reaction using a system of plastic scintillators and photomultiplier. The goal of the work, feasibility study of a possibility of creating an energy storage and conversion model according to the scheme with a neutron pumping. The objectives of this work are presented on this slide. The first objective allows us to determine the parameters and criteria that allow us to achieve an inverse population of levels of nuclei of active medium with following generation of gamma radiation. The creation of a neutron and CFD model of the installation allowed to optimize the installation parameters, setting up the operation of plasma neutron source on the blanket, and leveling of sets of the radial and axial energy release fields. The third objective makes it possible to design a variable geometry beam shaping assembly, consisting of a system of moderating filters and selective plates designed to form neutron flux with the spectral parameters required for pumping the active medium. To assess the possibility of energy accumulation in the isomeric states of the nuclei of gadolinium-156M isotope during pulsed periodic pumping, a system of differential equation was solved, in which the neutron flux density is a function of time. The frequency, duty cycle, and average energy of the neutron spectrum in a pulse varied during the simulation. The solution of the system of equations made it possible to determine the conditions under which the concentration of nuclei in isomeric states becomes greater or equal to the concentration of nuclei in the ground state when exposed to neutrons with a given flux density. The estimates have shown that when neutrons with a flux density of 10 to 13 degrees are exposed to active medium formed by gadolinium, the concentration allowing to achieve inverse population of levels of nuclei of the active medium with a following generation of coherent gamma radiation is achieved in a few tenths of seconds. Certified programs, Serpent and SolidWorks, were utilized to perform neutronic, thermophysical, and heat hydraulic studies of the blanket parameters. For the first step, input sets of plasma neutron source parameters were taken from article whose title is shown on this slide. In the second step, CFD modeling was performed for both the basic blanket loading option and the optimized option, taking into account the spatial energy distribution from the result of neutronic and thermophysical simulation obtained in the first step. The main objective of the optimization process was to determine the temperature mode for blanket cooling by helium flow, construct temperature fields, search for the temperature extremes, and estimate the offsets of the energy released fields in the blanket volume. The results obtained from this computational stage will be used to prepare datasets of additional neutronic, thermophysical, and hydraulic data to validate the results in new simulations using the model which includes blanket, plasma neutron source, and variable geometry beam shaping assembly. The flow simulation package in SolidWorks program was used for CFD modeling. The heat sources are fuel blocks and reflector blocks. The heat release of plasma neutron source was not taken into account due to the presence of its own cooling system. CFD modeling was carried out on 1/6 of total blanket to optimize the calculation time. The slide shows the temperature distribution for the basic blanket loading option. The coolant is supplied from below at a temperature of 573 degrees Kelvin. The initial temperature of solid body of the model is equal to the temperature of supplied coolant, assuming that the blanket was preheated by pumping coolant through it. The pressure and the velocity of the coolant at the outlet of the blanket were chosen as a boundary conditions, which amounted to 6 megapascals and 35 meters per second. To determine the optimal values of these parameters that provide the required temperature characteristics of the core, several iterations of CFD modeling were carried out. The maximum temperature of the model is observed at an altitude of 2.43 meters. The temperature of the fuel blocks located on the periphery is significantly lower due to direct contact with the cold reflector. The maximum fuel temperature for this model was 1623 degrees Kelvin. Thermophysical and heat hydraulic optimization of the blanket was performed according to the energy distribution profile along the radius by changing the volume fraction of dispersed phase, which was 17% for the basic non-profiled load. The calculated heat emissions of each block are applied in a new iteration of CFD modeling, the results of which you can see on the screen. The coolant pumping mode remained the same. The maximum temperature of fuel decreased to 1582 degrees Kelvin. Utilizing the blanket loading scheme result in a more uniform radial energy distribution profile. Furthermore, the peak values of the energy distribution in the region with the maximum temperature are reduced by 7.5% in comparison to the base non-profiled variant. The maximum fuel temperature for the profiled and non-profiled core was 1623 and 1582 degrees Kelvin, respectively. Optimization made it possible to reduce the maximum temperature in the cross-section by 40 degrees Kelvin. The results of calculation in the axial direction also demonstrate a decrease in temperature gradients in the multiplying part and the area of the plasma neutron source and variable geometry beam shaping assembly placement. Overall, the obtaining parameters of the devices under study demonstrate satisfactory agreement with the parameters of the reference facilities of this class. The results obtained in the work confirmed the possibility of using Serpent and SolidWorks programs to develop a complex model of a multiplying blanket with a plasma neutron source. Synergy among the components of the installation proposed in this work, which combines variable geometry beam shaping assembly, an active medium, and a subcritical blanket with plasma neutron source, creates a possibility to employ this system in the development of a technique that generates radiation with parameters suitable for use in pulsed energy. In this study, the parameters allowing to achieve the inverse population of the levels of nuclei of the active medium with following generation of gamma radiation are determined. Neutron and CFD models of the device were created, which made it possible to optimize the neutron and thermophysical parameters of the installation. The configuration of a variable geometry beam shaping assembly designed for formation of a neutron flux with the spectral parameters required for pumping the active medium is developed. The scientific foundations and principles of designing experimental devices generating coherent gamma radiation according to the scheme of neutron pumping of active medium are formulated. Thank you for your attention and goodbye.
I am Abel Martinez from the University of Sonora. I work in the Department of Investigation in Polymers and Materials, and I want to expose for you this work. This is our work of investigation. The name of the work is the determination of thermoluminescent kinetic parameters of noble magnesium oxides, chemically modified with samarium and lithium, obtained by glycerin-based solution combustion synthesis. I want to expose the main thermoluminescent characterization and the methods for obtain the kinetic parameters. A little introduction is about the technique. The technique is the solution combustion synthesis, and it's a technique efficient to obtain polycrystal materials, and it has advantage over other techniques due to its low cost and speed and the high performance of mass that you can obtain. The reagents used to synthesize this material are magnesium nitride hydroxide, lysine, samarium nitride hydroxide, and lithium chloride to obtain magnesium oxides chemically modified with samarium and lithium. The steps for obtaining the material are the next. First, we have to weigh the reagents and pour the reagents into the beaker in solution with deionized water. The solution is magnetically stirred at 360 RPM for 30 minutes, and after that the solution is heating at 200 degrees Celsius for 40 minutes, and then at 500 degrees Celsius until the combustion. When the combustion is finished, we obtain the solid, and the solid is poured into the agate mortar for the homogenization, and after that the powder is prepared for the annealing, and the annealing is at 900 degrees Celsius for 2 hours, and then the powder is ready for the characterizations. In here we can observe the thermoluminescent glow curve for this material. This is a main characterization for this type of materials, and we can observe that there are two maxima. The first maxima is around 150 degrees Celsius, and the second maxima is around 270 degrees Celsius. We can observe too that the intensity of the thermoluminescence is increasing with the dose. There are a relation with the dose that the material was exposed. Here we observe the evolution of the glow curves and the normalized integrated thermoluminescence as a function of the number of irradiation cycles. The idea was observed in this characterization if the intensity of the thermoluminescence was changing, and we use 12 cycles to this characterization, and we can observe that the material for the 12 cycles has no a big difference between the cycles, and we can say that the material is reusable for almost 12 cycles. And here we have the normalized integrated thermoluminescence, and And we have the standard deviation that corroborates the first affirmation that I said before. And this is the figure number 3, and it shows the graph of Tm as function of T stat for this material. In carrying out the experiment of the McKeever's well headings, it can be seen that for the T stop of 100 degrees Celsius, there is a behavior of points in the form of a flat line, and that suggests a field order kinetics. However, it's necessary to say that there is a significant contribution of the fading in this temperature range, while for values between 110 and 210 degrees Celsius, the flat region is observed and is followed by scaling in the form of a prolonged inclined line. This tendency can be related to a field order kinetics for the flat region, while the tidal region will suggest a contribution from other types of kinetics. For example, mixed kinetics, and for the remaining values above 210 degrees Celsius, it can be a flat line followed by the same behavior. This is low, and it will be suggest the same behavior mentioned before of the previous growth of points. This is the figure number 4, and this is the graph for the initial rise method for calculating the activation energy. The graph was made using the 15% of the maximum intensity of the first maxima of the globe curve. And the activation energy is equivalent to the slope of the graph. The value of the activation energy I will expose in a next figure. And these are the values obtained by the graphic method. These values are obtained dividing the globe curve into parts, and these values are used for determining the graphic geometric factor. And the geometric factor is used for different equations proposed by different authors to calculate the different parameters, like the activation energy or the frequency factor, and these are the different values obtained by this method. It's important to say that the geometric factor is an approximation for the kinetic, for order of the kinetic. Depending on the value of this geometric factor, is supposed to be a different kinetic, different kinetics, and it's important to mention that the equations of the different authors are approximations, and I will expose the different values obtained in the next figure. The geometric factor is suggesting first order kinetics. The different methods used in this work, the activation energy is different but is a very similar result between the methods. As a final result, the frequency factor has different magnitude orders, but it's a good approximation for these methods. And the conclusions for this work. The first conclusion is that it was possible to obtain for the first time through the method glycine-based solution combustion synthesis magnesium oxidized phosphorus powders chemically modified with samarium and lithium. And the dose response was shown to be linear for the range of doses applied. However, for reason of the time, I decided to not include in this presentation. Magnesium oxidized phosphor, chemically modified with samarium and lithium, show a response linear to the dose. In addition, the reproducibility and reusability of the thermoluminescent signal was observed. The signal and the stability over the time of the aforementioned signal was observed. This stability was due to the existence of the highest temperature peak, and the thermoluminescent characteristics obtained in this work for the synthesized materials suggest that they are candidates for application of thermoluminescent dosimetry of ionizing radiation for intermediate and higher doses, such as used in the medical area. As well in the personal dose monitoring, and according to the results obtained from the dose response. This is the bibliography consulted in this work, and also here is my email for any question. And thank you. This is all for me.
Buenas tardes, mi nombre es Gonzalo García, soy profesor ayudante e investigador de la Universidad Politécnica de Madrid. En primer lugar me gustaría dar las gracias a los organizadores del Congreso por la oportunidad de presentar nuestro trabajo, así como a todos los asistentes. Mi presentación será en castellano, aunque las diapositivas están en inglés. Sorry for the English speaker, my presentation will be in Spanish, but the slides are in English, so if you need further explanation, please send me an email or a message. Este trabajo ha sido parcialmente apoyado por el proyecto Euratom 2021 de la Unión Europea. Respecto del contenido del trabajo, en primer lugar, una breve motivación sobre los métodos de aplicación de dosis en protonterapia, el propósito y los objetivos, los modelos utilizados, principales resultados y un breve resumen. Y finalmente, pues no tenemos ningún conflicto de interés con respecto a este trabajo. La protonterapia es un tipo de radioterapia donde se utilizan protones en lugar de los fotones convencionales para el tratamiento de tumores. La ventaja fundamental de los protones frente a los fotones, como se aprecian en esta figura, es que mientras que los fotones depositan dosis antes y después de la zona a tratar, los protones, al ser partículas cargadas y pesadas, pues se detienen aproximadamente en un punto conocido, denominado pico de Bragg, con lo cual, pues utilizando diferentes energías, es posible cubrir la zona tumoral mediante el denominado pico de Bragg extendido, el SOVP, y de esa manera obtener una mejor conformación de dosis. En la figura de abajo se puede apreciar la interacción de protones con el agua, donde en función de la energía pues se detienen antes o después en el phantom, pero se detienen. Desde el punto de vista de la terapia, bueno, pues la mejor conformación lo que genera es una posible mayor control del tumor, disminuyendo las complicaciones por la toxicidad debido a la dosis fuera de las zonas tumorales. Esto ha hecho pues que la protonterapia en los últimos años esté en un gran incremento alrededor del mundo, con 108 centros en operación, 38 adicionales en construcción y 33 en distintas fases de planificación. En España, los dos primeros centros comenzaron a funcionar en Madrid a finales de 2019 y principios de 2020. Actualmente hay un centro en la fase de construcción en el norte de España, que será el primer público, financiado con fondos europeos, y además hay otros 10 centros públicos también en construcción, lo que son las estrellas rojas, en diferentes ciudades de España, gracias a la donación de la Fundación Amancio Ortega, que es el dueño de la empresa Zara. Como se puede apreciar en esta diapositiva, ha habido una evolución desde métodos pasivos, pasando por métodos activos, y ahora una serie de nuevos métodos, fundamentalmente basados en estos métodos activos o de scanning. Los métodos pasivos, que comenzaron con el origen de la protonterapia, estaban basados en muchos elementos metálicos que generaban una radiación secundaria importante, diferentes colimadores, etcétera, etcétera. Actualmente la mayoría de los centros disponen de métodos activos basados en scanning, mediante conjuntos de imanes, y la profundidad se obtiene mediante la energía, y basados en estos métodos activos pues hay diferentes nuevos métodos como flash, proton mini beams y métodos híbridos en desarrollo. Se puede apreciar cuando se aplica un tratamiento, lo que se hace es dividir el tumor en diferentes láminas. Cada lámina se corresponde con una isoenergía y esa lámina es cubierta por diferentes corrientes de protones, que es lo que se llaman los spots. Estos puntos son los puntos donde se aplicaría la dosis mediante protones. Como se puede apreciar, cuanto más próxima es la capa a la entrada de los protones en el paciente, más spots es necesario, puesto que los protones tienen menos energía. Por tanto, para depositar la misma dosis es necesario más spots que en la capa distal, la última, donde los protones tienen más energía para alcanzar esa profundidad y es necesario menos spots. cada capa es cubierta por diferentes spots, como se ven los azules, y los rojos serían la zona entre tumor y no tumor, que es la zona donde puede haber problemas desde el punto de vista de conformación de la dosis, puesto de lo que se trata en cualquier tratamiento ideal es depositar o atacar las células tumorales preservando al máximo el tejido sano. Aquí se puede apreciar lo que es el ensanchamiento que se produce en la corriente de protones según va alcanzando una profundidad en agua. Debido a las interacciones, básicamente nucleares, desde un ancho inicial pues se pasa a una dispersión final, justo antes de pararse. Aquí es donde se produciría el pico de Bragg. Los métodos pasivos, pues lo que hacían era aplicar un campo más o menos cuadrado o rectangular para que cubriera toda la forma del tumor, y se utilizaban diferentes conjuntos de colimadores. Los métodos activos lo que van haciendo es depositando spot como un pincel, pero hay una zona que está entre tumoral y no tumoral. Los activos con colimador lo que utilizan es el sistema de pencil y se utiliza el colimador para perfilar aquellos spots que podrían estar fuera de campo. De esta manera, en los métodos pasivos tenemos dosis fuera de campo y además una activación. En los métodos activos tenemos una pequeña dosis fuera de campo, y con los métodos mixtos o híbridos la dosis fuera de campo se reduce un poco, pero se tienen que utilizar colimadores, aunque no es un campo total, sino que son en pequeños puntos donde los protones interaccionan con los colimadores. Estos métodos activos con colimador son totalmente diferentes, no tienen nada que ver con los métodos pasivos, donde se utilizan diferentes conjuntos de bloques con espesores pues muy grandes y específicos de cada paciente. En los métodos híbridos se utiliza un solo colimador por cada uno de los campos. El propósito de este estudio ha sido analizar cómo se activan estos colimadores y cómo se pueden manipular y reutilizar. Para ello, bueno, pues se han utilizado los colimadores que se pretenden utilizar en el centro de protonterapia Quirón. Estas son las características, con un diámetro exterior de 20, un espesor de 4,5 centímetros y un diámetro interior aproximado de 1,6, que es lo que cubriría el tumor. La composición es básicamente cobre, con pequeñas cantidades de estaño, plomo y zinc. Evidentemente es parecido al latón, pero no es latón, y es parecido al bronce, pero no es bronce, como se puede apreciar. Son aleaciones específicas. ¿Qué es lo que pasa cuando los protones interaccionan con los colimadores? Pues se producen reacciones de espalación, generación de neutrones, y estos neutrones activan este equipo tanto mediante espalación directa como por captura neutrónica. Hay isótopos que se producen directamente por la interacción de los protones, y al final lo que tenemos es una activación mientras hay irradiación, y cuando dejamos de irradiar pues hay un decaimiento. Hay producción de radioisótopos y desaparición porque son isótopos radioactivos. Uno de los más importantes es el cobre, primero porque el cobre tiene diferentes isótopos que se activan de diferente manera. Segundo, porque a partir de los isótopos del cobre se generan muchas especies radioactivas. Y tercero, porque los isótopos del cobre natural reaccionan tanto con los protones como con los neutrones. Se activan de diferente manera. Con lo cual, bueno, pues aquí está la zona en la que se producen isótopos radioactivos en función del número de neutrones y el número atómico, el número de protones. Esto es lo que se llama la carta de radioactividad. El método utilizado, o la metodología, ha sido mediante los métodos de Monte Carlo, utilizando el código Phipps, y dentro del código Phipps el módulo general, donde se ha utilizado la simulación del transporte de partículas, y los resultados se han implementado en un segundo módulo que se llama el de Chain, donde se hacen cálculos de inventario dentro del mismo código FIPS. FIPS es un código de la JAEA, que es la Agencia de la Energía Nuclear de Japón. Este es el modelo donde se puede apreciar la geometría. Este es el colimador con el hueco, con la forma del tumor a tratar, y el cubo de agua trasero pues simula al paciente, porque la interacción de los neutrones y los protones con los pacientes se puede utilizar mediante el agua. Los materiales utilizados, pues aquí se ve el porcentaje en el colimador, los tipos de celdas, y aquí se ve pues ya cómo la corriente de protones va por el aire generando algunos pequeños protones, bastantes neutrones y bastantes fotones. El modelo de irradiación es mediante pencil, mediante spots puntuales con energía de 200 MeV, y aquí se ve, bueno, pues como los protones chocan ligeramente con el borde del colimador y el resto pasan para tratar el tumor. Los neutrones que se generan se puede ver en esta parte, en este gráfico, y los fotones en el gráfico de abajo en coordenadas Z, Y, y aquí, bueno, pues la afluencia en función de la profundidad. Como resultado de estas interacciones, pues se producen campos de radiación, tanto de protones. Aquí se ve la intensidad de los diferentes campos para neutrones, fotones, y bueno, pues se podrían producir algunas pequeñas cantidades de deuterones y alfa, pero como se ve es secundaria. Lo principal son los neutrones y los fotones. Desde el punto de vista de los isótopos generados, pues los más importantes han sido isótopos del plomo, por ejemplo el plomo 208, algunos isótopos del estaño, por ejemplo el estaño 120, y sobre todo isótopos del cobre y isótopos del zinc, como son el zinc 64 y bueno, pues distintos isótopos del cobre. Estos son los nucleidos madre y los nucleidos hijos que se han calculado, y el código da la concentración en número de partículas o de radioisótopos generados, por ejemplo, de cobalto 60, de cobalto 58, por protón de la corriente. Aquí se ve la actividad, donde la parte roja se corresponde con la irradiación y la pieza se va activando hasta que se termina la irradiación, que suele durar 2 minutos, y al cabo de la hora pues la actividad ha bajado prácticamente un orden de magnitud. Como se ve, pues el calor fundamental viene de la desintegración beta y de la gamma, y prácticamente nada de alfa. En términos de dosis, la dosis al final de la irradiación es de 0,32 microsievert hora, y al cabo de una hora prácticamente está en niveles ambientales. Como se puede apreciar, bueno, pues aquí la actividad al cabo de un día. Hay que tener en cuenta que estas piezas se utilizan una vez al día porque son específicas de cada paciente y es en cada sesión. Con lo cual, pues prácticamente al cabo de 24 horas la dosis es 0 o compatible con 0. Aquí está el estudio de las diferentes zonas de activación de la placa, y para concluir, como sumario, podríamos decir que los métodos híbridos utilizan sistemas de pencil con un colimador específico, que las piezas individuales o colimadores están basadas en cobre, aleaciones de cobre, y que la manipulación sería totalmente segura. Se ha calculado en un escenario conservador sin decaimiento, que la dosis y exposición está dentro de los límites del background o los límites naturales, con lo cual el almacenamiento, desclasificación y la reutilización estaría dentro de la seguridad. Y bueno, pues hay otros trabajos en marcha basados en parametrización y otros estudios de otros materiales. Finalmente, pues muchas gracias por la atención, gracias al proyecto NN2 por la financiación, y bueno, pues cualquier pregunta, ahí tienen mi contacto, y gracias de nuevo.
Gracias por su asistencia. Los esperamos mañana desde las 7 de la mañana.